So this is the free response section from the 2017 AP Calculus exam. This is the calculator section. So let's look at number 1. It tells us about a tank where A of H is measured in square feet, H is in feet. The function A is continuous and decreases as H increases. And they give us the selected values. So part A says use a left Riemann sum with 3 subintervals, 1, 2, 3, indicated by the data in the table to approximate the volume of the tank and indicate units of measure. So this is a nice straightforward question. So we're just using a left Riemann sum. Remember, each rectangle is delta x times the height given at the left. So between 0 and 2, my delta x is 2 times the guy to the left, which is 50.3, plus my next rectangle, 2 to 5 is 3, times my height to the left, 14.4, plus from 5 to 10, delta x is 5, and then again evaluated at the left. We just add these all up in the calculator, and we should get 176.3 units of measure. If this is area, and we're integrating, right, finding the area under the curve, that is now volume. And it tells us to approximate the volume. So volume is 3 dimensions, feet cubed. Area is squared. 1 dimension is just 1. Then it asks, does the approximation in part A overestimate or underestimate the volume of the tank? Now, if you forget, you could always draw a simple graph. Notice, and it tells us it's decreasing, but see, y is decreasing as the input increases. And so you could even just sketch a decreasing curve and draw your vertical lines from the left attached to the right. From the left attached to the right. Notice your rectangles are above the curve. Therefore, if it's a decreasing function with the left Riemann sum, it is an overestimate. And you can write that. Since A of H is decreasing and this is a left Riemann sum, the volume is an overestimate. You also could have went ahead and found the value of a right Riemann sum, right? Delta x times the right, so then 3 times this, 5 times this guy, and you would have seen that that number would have been less than this number, and so you could have, from there, assessed that this is an overestimate, where the right Riemann sum is an underestimate. So either draw yourself a sketch or find the right Riemann sum to compare. Okay, part C. The area in square feet of the horizontal cross-section at height h feet is modeled by the function given by, so we have this whole new function. Based on this model, find the volume. So again, they give us the area, an area function in square feet, and they want to find the volume. Well, we know if we have area function and we want to find the volume, we need to integrate. So we have volume equals, and it's from 0 to 10, right, from here, 0 to 10. 0 to 10 of this function, I won't rewrite it, I'll just write f of h, dh. And it's important to write it, volume equals, all of this. You can plug this into your calculator, and you should practice doing so, and your answer should be, and remember, this is Math 9 in the calculator, Math 9 in the calculator, and you get 101.325. It is volume, so feet cubed. Okay, so far these were pretty straightforward. This one may be a little tricky. Water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 foot per minute. Using the model from Part C, well, here's our model. Find the rate at which the volume of water is changing with respect to time. So we want to know when h is 5 feet. We know the derivative of h with respect to t is 0.26 foot per minute. And we want to find the rate, right, derivative of volume with respect to time. So we have a related rates problem. And with related rates, we always have one variable. When something is, we know the value of one rate, we're looking for the value of another rate. And we know for related rates, the next step is to have some kind of formula that I can take the derivative of and end up with dH over dt and dV over dt. That's our goal for all related rates problems. So it says to refer to the model from Part C. That's why it was important to write this here. I see this, there's no dV, there's no V here, so I won't get dV over dt. But when I was finding the volume using this, I knew volume equals all of this. Oh, if I differentiate this left side, I'll get a dV over dt. And if I differentiate f of h, I will get a dH over dt. So this is what we are finding the derivative of. So I will rewrite it. This is my volume function. Really, I should have this whole thing written, right? This is this. And so when I find the derivative of the left, well, that's just my dV over dt. When I find the derivative of the right, well, by fundamental theorem of calculus, I know the derivative and an integral are inverse functions, so it just cancels out that integral. And I'm left with just f of h, which is this formula, 50.3 all over e to the 0.2h plus h. And this is dH with respect to dt, right? Because this is h, so dH over dt. Now I can go ahead and plug in 5 for each h and 0.26 for dH over dt. So dV over dt equals 50.3 e to the 0.2 times 5 plus 5 times 0.26. Plug this all into your calculator and we get dV over dt equals 1.694. It's volume per minute, right? Derivative of volume with respect to time. So it's F cubed, that's volume with respect to time per minute. On the AP exams, especially when using a calculator, I would play it safe and always round at least 3 places.